Alright, so let's finish up our discussion of the graphs of the trig functions by looking at the secant and cosecant functions. This is section 4.4, by the way, graphs of secant and cosecant. Secant is 1 over cosine, right? And cosecant is 1 over sine. And so consequently the graphs of secant and cosecant are very, very intimately related to the graphs of cosine and sine respectively. So I want to show you these graphs in Desmos so that you get the idea. So let's look at y equals, we'll start with the secant function, secant x. Okay, what I want to point out is if I graph this together with the cosine function, y equals cosine x, then you kind of see the relationship, right? So the red graph is secant, right? So that's the secant function. But if you look at it with cosine, it's interesting. Whenever cosine is 1, secant is 1, right? They kiss at all of those points. But also they kiss whenever cosine is -1, right? Whenever cosine is -1, secant is -1. And that's because secant is just 1 over cosine. So if cosine is 1, then secant is 1 over 1, which is 1. If cosine is -1, then secant is 1 over -1, which is -1. If cosine is 0, then secant is undefined, right? Secant would be 1 over 0, which is undefined, which is why you have this vertical asymptote at pi over 2, because cosine is 0 there, right? So that gives us a kind of an easy way to graph a secant function. If you want to graph a secant function, what you can do is just start off by graphing the corresponding cosine function, and then wherever you have these kind of maximum values, you're just going to draw a little parabola looking thing going up, right? And whenever you have these minimum values, you're going to draw a little parabola looking thing going down. And whenever you have zeros, you're going to draw vertical asymptotes. That's one way to do it. Another way to do it is to just graph it directly. Doing so would require you to kind of memorize that for the secant function, one full period, and let's talk about the period for a second. So if you do from -pi over 2 to pi over 2, that's one copy of the parabola, but it's only the copy of the parabola opening up. If you want to get the copy of the parabola opening down as well, then you actually need to go all the way from -pi over 2 to 3 pi over 2. So the period is still 2 pi, but it's not as simple as just squeezing the values between 0 and 2 pi. We would actually squeeze the values between -pi over 2 and 3 pi over 2. Which is why I actually think it's easier to just graph the cosine function, and then you can graph the sort of corresponding secant function, I suppose. But I'll show you both ways. And you can kind of pick the one that you like the best, I suppose. But anyway, that's the secant. Cosecant has a similar relationship with the sine function. So there's y equals cosecant x, and if I graph that together with y equals sine x, then again you can see that wherever sine is 1, cosecant is going to be 1. Wherever sine is -1, cosecant is going to be -1, and you're going to have parabolas going up, parabolas going down. I'm calling them parabolas. They're not parabolas, right? But they kind of have that basic sort of shape, I suppose. But anyway, and then wherever sine is 0, cosecant is undefined, and so it has a vertical asymptote. So it's got vertical asymptotes at 0, pi, 2 pi, etc. Cosecant's a little more straightforward in terms of its period. I mean, its period is 2 pi, the same thing as secant, but you get kind of one standard copy of the graph just by going from 0 to 2 pi. Whereas with the secant function, remember, we had to go between -pi over 2 and 3 pi over 2, right? So cosecant's a little bit easier in that regard. But the same sort of strategy applies to cosecant. If you just graph the corresponding sine function, then you get a really good idea of what this cosecant function is going to look like as well. So, so I want to walk you through a few examples. Okay. So let's graph a few things. Let's do f of x equals 2 cosecant x. And I'll give you two sort of methods for this, I suppose. Okay? So, so method 1 would be to graph y equals 2 sine x, right? Just change out the cosecant for a sine. Graph this thing first, and then you'll have a good idea what the cosecant function looks like. So to graph 2 sine x, right, we would say 0 less than or equal to x less than or equal to 2 pi. So that gives you your starting and stopping point. And the period is obviously 2 pi. And therefore, the thing that you're going to add is 2 pi divided by 4, which would be pi over 2. Okay? Make a little table of values. 0, pi over 2, pi, 3 pi over 2, 2 pi. And then remember, sine starts at 0. It goes, oh, but I'm going to be doubling, right? I'm going to be doubling. So it starts at 0, and then it goes up to 1. Then it goes back to 0, down to -1, and then back up to 0, right? So that's what the sine function does. So, so let me do, oh, here we go. I've got another, I wanted to grab another color, but I'll do the sine function in blue, and then I'll do the actual cosecant function in red, right? So that you can see see the difference. But okay, so we're gonna have pi over 2, pi, 3 pi over 2, 2 pi. Okay, 1, 2, 1, 2. All right. So the sine function looks like this. Right, and it's going to keep doing this, you know, forever and ever and ever. It would have been better maybe if I had done that with a dotted line, but anyway. So the cosecant function then, right, in red, it's going to have asymptotes whenever the sine function is 0. So that happens here, and here, and here, right? So all of the integer multiples of pi. And then it's going to be 1 wherever sine is 1. It's going to be -1 wherever sine is -1. So, and then it does kind of the opposite thing of the sine function. So it does that, and it does that. Okay, and that's one copy. That's one copy of the cosecant function. You can, of course, extend this, right? So you're going to have another copy here. And then another one going up over here, right? And this is going to keep going on forever and ever and ever. But again, you can see that because, you know, the sine function would do the same thing, right? So, so anyway, that's method 1. Now here's another way to do the problem. You could just graph y equals 2 cosecant x directly, right? You can just graph it directly. And in this case, that's not terribly complicated because you just have, you don't have any phase shifting going on or anything like that. So you would let x be between 0 and 2 pi. So then you know that the period is 2 pi. and then you know that you're going to add 2 pi divided by 4, which is pi over 2. So a lot of this work we've already done, of course. Now, so we're going to plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. You're going to plug those values into your calculator into the cosecant function directly. Okay? And when you do, when you plug in 0, you should get undefined. When you plug in pi over 2, you should get 1, except you're going to multiply it by 2, so I guess 2. When you plug in pi, you should get undefined. When you plug in 3 pi over 2, you should get -1, but then you'll multiply it by 2 to get -2. And then if you plug in 2 pi, you should get undefined again. Okay? And so what does this look like? Oh, I should have done that a little less. Not quite as big, I guess, but anyway, that would look like this. So at 0, you've got an asymptote. At pi, you've got an asymptote. At 2 pi, you've got an asymptote. At pi over 2, you're up here at 2. And at 3 pi over 2, you're down here at -2. And then if you just remember what the cosecant function looks like, you know that you've got these little parabolas. Not really parabolas, but for all intents and purposes, we can think of them like parabolas. And that's that, right? So, so that's method method 2, right? So 2 ways to do it. I think for the cosecant function, either way is like equally easy. But for the secant function, it's a little trickier. Okay, so for the secant function, I'm definitely going to stick with method 1. And so for the next 2 problems that I show you, I'm not going to work it out both ways. I'm just going to do method 1. But for the secant function, it's trickier because when you graph the secant function, you don't pin the argument between 0 and 2 pi. You pin the argument between -pi over 2 and 3 pi over 2. And so for me, that's just one more thing that I have to memorize. And I'd rather not, like I'd rather memorize as little as possible. So I think method 1 is generally speaking, easier to do. So let's do a secant. And we'll make this one interesting. 1/2 x plus pi over 2. So we've got a phase shift. We've also got a horizontal stretch. Okay, so let's do this. So I'm going to graph y equals cosine of 1/2 x plus pi over 2. And this we already know how to do, right? So I'm going to pin 1/2 x plus pi over 2 between 0 and 2 pi, and then I'm going to solve for x. So that would require me to first subtract pi over 2 through the inequality. 2 pi, so that's 3 pi over 2. And then multiply by 2. So there you go. And then you can kind of tell, okay, so the period's going to be 4 pi. You could also have told that because 2 pi divided by 1/2 is 2 pi times 2, which is 4 pi. But anyway, so the period's 4 pi. So period is 4 pi. So you're going to add 4 pi divided by 4, which is just pi. That's kind of nice. Okay, so starting at -pi, then I'm going to add pi, and again, and again, and again, and then I land at 3 pi right where I should. Now cosine starts at 1, and then goes down to 0, and then down to -1, and so forth. And we're not multiplying anything out here or adding anything, so so this should go 1, 0, -1, 0, 1. Okay. So negative pi, 0, pi, 2 pi, 3 pi. Okay, and then 1 and negative 1. So again, I'll do the cosine function in blue. I'll try to do a dotted line this time though. So at negative pi, we're up here at 1, 0, 0, pi, negative 1, 2 pi, 0, and then 3 pi, we're back up at 1. Okay, so it's going to look something kind of like that. This thing is going to keep going forever and ever and ever though. So by the time we get over here to 4 pi, so let's say that that's 4 pi, it's going to be back down to 0. And maybe this is negative 2 pi, right? It's going to be back down to 0. Now, the secant function is therefore going to have vertical asymptotes here, 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 right, and here, and it's going to look kind of like this. So we actually got 1.5 copies of the secant function that way. Instead of just one copy, we got 1.5 copies. That's okay though. All right, you get the idea of how to go about graphing that. So so that's that one. Do I need to show you any more? Yeah, I'll give you one more. We'll throw in all of the possible transformations you could get. So let's graph f of x equals 1 minus 1/2 cosecant 3x minus pi. So we've got some horizontal compressions, some phase shifts, some vertical compressions, and then a vertical translation. So so lots of stuff going on. But I'm going to do this the same way that I did the previous one, right? So what I'm going to do is graph y equals 1 minus 1/2 sine of 3x minus pi. And to do that, I'm going to trap the argument between 0 and 2 pi. And then solve for x. So I would add pi and then divide by 3. That's kind of interesting, right? So what is the period? Well, looking at the original function, the period should be 2 pi divided by 3. Looking at it this way, pi minus pi over 3, yep, is 2 pi over 3. So the period's 2 pi over 3. What are we going to add? We're going to add 2 pi over 3 divided by 4. That would be 2 pi over 12, or in other words, pi over 6, right? So we're going to add pi over 6. Starting at pi over 3. So pi over 3 plus pi over 6, this would be 3 pi over 6, so in other words, pi over 2. And then you add another pi over 6, you get 4 pi over 6, or in other words, 2 pi over 3. You add another pi over 6, you get 5 pi over 6. And then you add another pi over 6, and you get 6 pi over 6, or in other words, just pi. So that's working out pretty nicely. Now the y values are going to follow the same sign pattern, 0, 1, 0, negative 1, 0. But we have, first of all, we have to multiply that by negative 1/2, and then second of all, we need to add 1. So 0 times negative 1/2 is still 0, plus 1 is 1. Here we would be at 1. 1 times negative 1/2 is negative 1/2, plus 1 is positive 1/2. Here we'd be back to 0. Here we'd be down at negative 1. Negative 1 times negative 1/2 is positive 1/2. 1/2 plus 1 is 1.5, 3 halves, right? And then here we'd be back at 0. Okay, so let's graph that sine function. Now it's been a while since we've done some kind of tricky work here, but there's only the distance between pi over 3 and pi over 2 should only be pi over 6, right? Because that's what we were adding each time. And so if I plot pi over 3 right here, and then I plot pi over 2 equally spaced out from it, that's not quite right, because the distance from 0 to pi over 3 should be 2 pi over 6, right? So what I'm really going to do is mark out the pi over 6's, right? So there's pi over 6, 2 pi over 6, which is pi over 3, 3 pi over 6, which is pi over 2, right? And then this is working out a little nicer. Then I'm sure the spacing looks the way it should, right? 2 pi over 3, 5 pi over 6, and then pi. Okay, and then I've got, well, I've got 1/2, 1, and then 3 halves will be, you know, right there. So I've got 1/2 and 3 halves on there. Okay, so let's plot the points now. So I've got pi over 3, 1, pi over 2, 1/2, 2 pi over 3, 1, 5 pi over 6, 3 halves, and then pi, 1. Sure enough, there's that little sine curve. It's been flipped over though, right? Because of that negative sign right there. Okay. I could continue with this pattern, like I know at pi over 6. See, and here's another reason why it's important to get the spacing right. Because the next part doesn't end up at 0, it ends up at pi over 6, and then back down to 1 there. Anyway, but I get this sort of thing happening, right? So maybe at the next one it'd be back down to 1/2, right? And this is going to keep happening forever and ever and ever. So that's the sine function, but I wanted to graph cosecant, which I'm going to do in red, okay? So usually I would say wherever you have zeros, you're going to have vertical asymptotes. Obviously you don't have zeros here, but it's like it's where the sine function would be 0 if we hadn't done any transformations or anything. So in other words, it's kind of like 1 has become the new 0 because we shifted the whole thing up 1 unit. So that means I have asymptotes here, 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 and so forth, right? Anyway, so the cosecant function is going to look like that, 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 and so forth, right? It's going to go on and on and on forever. Okay, so that's it for the graphs of secant and cosecant. And in fact, that's all I'm going to say about the graphs of these functions. Well, I mean, they'll come up throughout the course, but as far as doing like really intricate, like tricky graphing of these things, this will kind of do it for that particular section of the class. So I'll see you in the next one.